Hi, so we're going to be learning about acids and bases. We can start off with connecting to the real world. The Bracken Cave near San Antonio, Texas is home to 20 to 40 million bats. Visitors to the cave must protect themselves from the dangerous levels of ammonia in the cave. Ammonia is a byproduct of the bat's urine, and you're going to learn why ammonia is considered a base. We've learned about electrolytes, any substance that dissociates for a solution that can conduct, like ionics. Salt water would be a good example. And dissociate means to break into individual ions. Remember, ionics do this and covalents do not. And indicators, a substance that can change colors to tell us if a substance is an acid or a base. So let's learn about acids and bases in general. Acids tend to taste sour. They'll change color, an indicator. They can be strong or weak. pH is less than 7. They're corrosive and they react with metals. Examples: citric acid, right? Grapefruit, lemons, tannic acid, like in tea, and hydrofluoric acid, right? In our stomach, also is used as a cleaner. Bases tend to be bitter, can feel slippery. They tend to be like detergents and things like that. They'll also change the color of an acid base indicator. They could be strong or weak. The pH is above 7, and they're also corrosive. Things like antacids or the mortar in between the bricks. Also, drain cleaner. Again, lots of cleaners in general tend to be more basic or alkaline. Okay, so there's different definitions of acids and bases. Arrhenius defined acids and bases. Acids create H plus, and bases create or yield OH minus hydroxide. That's one definition or set of definitions. So here we can see hydrochloride is an acid. It has the H plus, right? It's going to create this hydronium. Sodium hydroxide has that OH, the hydroxide, and that's going to yield a hydroxide ion, and that makes it a base. However, the Bronsted-Lowry theory is a little broader. It defines acids as anything that can donate an H plus. A base is anything that can accept or gain an H plus. And I usually use this acronym ADBA. Acids donate, bases accept. That might help you. So in this situation here, you can see the NH3 becomes NH4. It gained an H plus. It gained or accepted an H plus. Well, to accept, right? So accepting, and let's look at the other side. The water in this case lost the H plus or donated. So acids donate and bases accept. So water is the acid in this case because it donated, and the base was ammonia because it gained ADBA. Acids donate, bases accept. Traditionally, we use formulas to know our pH, and pH is our main indicator of how something is an acid or a base. So it might look a little complicated, but we're going to keep it pretty simple. The pH is 9, then the H plus is 1 times 10 to the negative 9th. So the pH is related to the negative exponent. So 1 times 10 to the negative 4, the pH is going to be 4. If the pH is 5, then the H plus or the hydronium will be 1 times 10 to the negative 5. That's that relationship. Same thing with hydroxide. You can measure the amount of base, and it's still this exponential relationship. If the pOH is 11, then the concentration of the OH minus is 1 times 10 to the negative 11. That means if the pOH is 1, then the concentration is 1 times 10 to the negative 1. If the concentration is 1 times 10 to the negative 7th, then the pOH is 7. So if they give you that the H plus is 1 times 10 to the negative 5, how can you get to the OH minus? Well, first we have to take it in a couple steps. Let's take a look. Well, we know that the pH and the pOH has to add up to 14 because that's the total scale. If we know that the H plus is 1 times 10 to the negative 5, then the pH is 5. Now, if the pH is 5, what does this have to be to add up to 14? 9. Okay. So, again, if we only need to know one piece of the puzzle, we can solve the rest. Okay, so let's take a look. If the pH is 2, what's the pOH? Well, we know they have to add up to 14, so that makes the pOH 12. If the pOH is 7, then the pH has to be 7, because 7 plus 7 will make the 14. Okay, let's continue. How does this connect to the real world? Well, to test the diagnosis of diabetic coma, a doctor orders several tests, including the acidity of the patient's blood. Results from this test will be expressed in units of pH. Okay, so again, it's definitely relevant to our health. Our body must maintain homeostasis, and the pH range of that is very, very narrow. Let's take a look. So you can see, if there's a lot of acid, then there's less base. And remember, it's always going to balance out to that 14. So you can have equal amounts, 7 and 7 make 14, or you can have unequal amounts, but they will always add up to that 14 overall. Here you can see some common everyday substances and their pH. Things that are acidic, like coffee, tomatoes, lemons, stomach acid. Pure water is neutral, not tap water necessarily, but pure water. Blood is a little bit alkaline. And then things like baking soda, seawater, and then again, those detergents and cleaners tend to be more alkaline or basic. As the pH decreases towards 0, you get stronger acids. As the pH increases towards 14, you get stronger bases. As you get towards neutral, things get weaker in general. Also notice that we're increasing here by factors of 10. So you're getting stronger by factors of 10 or weaker by factors of 10. Neutralization. Excess hydrochloric acid in the stomach can cause heartburn and a feeling of nausea. Antacids like Tums, Rolaids neutralize the stomach acid and relieve the pain of acid indigestion. That's neutralization. So here's some common salts. A salt is a product of neutralization. We can tell we're at neutral by using acid-base indicators. Acid-base indicators will change color based on the pH. Again, pH is a measure of the H plus or hydronium. Basically, it's a measurement of acidity, is what we say in general. A universal indicator is a mixture of different indicators, and you get quite the rainbow. For acid-base indicators, it's all about the color change. So for example, and you can use table M as your reference table, methyl orange will be red at a pH of 3 or less, and from about 4.4 and above will be yellow. In between, it could be like an orange. Bromothiamyl blue, if it's below 6, it will be yellow. Above 7.6, it will be blue. In between, most likely green. So again, we're looking for this sort of parallel. Below 6, yellow. Above 7.6, blue. 4.5, right here, litmus will be red. Anything below 8.3, it will be blue. Bromocressyl green. Below 3.8 will be yellow, as you can see here. And above 5.4 will be blue. Thymol blue, anything below 8 will be yellow. Anything above 9.6 will be blue. So that's how you can read and use Table M. What color will phenolphthalein be in a solution with a pH of 6? Well, phenolphthalein, 6 is below the 8, so it will be colorless. Anything below 8 will be colorless. What color will phenolphthalein be in a solution with a pH of 11? Well, 11 is above 9. Anything above 9 corresponds to pink. Which indicator will be yellow at a pH of 10? Let's go through each one. Thymol blue. 10 will be above 9.6. So that would be blue, not yellow. Bromocressyl green. 10, pH of 10 would be above 5.4, and that would correspond to blue. Methyl orange. A pH of 10 would correspond to above 4.4. That would correspond to yellow. So at a pH of 10, which is above 4.4, methyl orange will turn yellow. And that's the correct answer for this. When you mix an acid and a base together, they will become neutral. Neutral has a pH overall of 7, and it means that the concentrations of H plus and OH minus will be equal. The reaction of an acid with a base produces water, neutral, that's why it's called a neutralization, and a resulting salt. Hydrochloric acid and sodium hydroxide produce salt and water. Sulfuric acid and potassium hydroxide will also produce a salt, potassium sulfate, and water. A neutralization can be used in something called a titration. So you have an unknown solution and a known solution, and you can keep mixing them until they balance out. You can see the neutralization using an acid-base indicator like phenolphthalein here. The solution of the known concentration is called the standard, or the titrant. And you'll keep adding until the indicator changes color at the end point. The process of adding a known amount of a known concentration to determine the concentration of another solution that's not known is called a titration. And the point of neutralization is the end point of the titration. And we're going to be learning more about this in our lab.